Clay has been described as the main culprit behind low resistivity pays. In addition to its effect on resistivity, clay exerts a special influence on a broad range of logging tools, all of which affect the outcome of your water saturation calculations. We will state from the outset that clay causes resistivity logs to read too low, and generally causes porosity logs to read too high. Let's take a look at a conventional suite of logging tools and see how clay can influence the readings from each tool. Let's start by describing the response of the spontaneous potential tool. SP deflection is a function of cation exchange capacity, formation water salinity, mud filtrate salinity, and formation water saturation. Clay causes a decrease in SP deflection due to a loss of ionic permeability. Clays can also have a strong influence on cation exchange capacity, and we can generalize by saying that clays, which exhibit high CEC levels, will produce a corresponding decrease in SP values. The gamma ray tool measures a formation's natural radioactivity. We can characterize gamma ray response by saying that the curve will deflect to the right, showing an increase in formation radioactivity due to the presence of clays and shales. However, it is important to remember that not all shales are radioactive, and some sands may also be radioactive or hot, thus masking their true lithology. In resistivity logging, clay decreases resistivity as a result of the surface charge of the clay and its associated bound water. Certain clays, such as montmorillonite clay and illite clay, have a higher cation exchange capacity than other clays, and subsequently will exhibit higher conductivity, and thus lower resistivity readings than other clays. Acoustic logging tools record the interval transit times of compressional sound waves. Clays are characterized by low acoustic velocities, and thus cause acoustic logs to record higher interval transit times. When the transit time of the reservoir's matrix is subtracted from the high transit time reading in a clay sand, the resulting acoustic porosity will lead to erroneously high estimates of porosity. Neutron tools derive their porosity readings from the concentration of hydrogen ions within the formation. In clean, clay-free sands, the neutron tool detects hydrogen ions that are contained in the water or hydrocarbons that occupy the pore spaces of the formation. However, with the addition of clay, the hydrogen ion count will increase. Hydrogen is a part of the crystal structure of all clays, as well as the irreducible water that is bound to the clay. Thus, in a sand-clay mixture, a portion of the total porosity recorded by the neutron log will reflect non-effective porosity occupied by bound water. A portion will reflect the atomic constituents of the clay mineral, and the remainder will be porosity that is occupied by producible hydrocarbons or water. Thus we see that clay will cause the neutron tool to record a higher porosity than is actually present. The density tool measures formation bulk density. When the density tool logs through a reservoir where clay density is lower than formation matrix density, the porosity derived from formation density will read higher than the formation's actual porosity. Conversely, when the density tool reads a clay density that is higher than formation matrix density, the porosity obtained from the density tool will be lower than the formation's actual porosity. When clay density is the same as matrix density, the log will measure only effective porosity. In summary, we can characterize log response to clays by saying that in the presence of clay, the spontaneous potential log shows a decrease in SP deflection. The gamma ray detects an increase in radiation. Resistivity values read too low. Acoustic porosity values read too high. Neutron porosity values read too high. And density porosity values usually read too high. So we can see that when we evaluate a low resistivity pay zone, it is not just the resistivity log which must be analyzed in detail. Most logs exhibit a response to clays that will skew the numbers used to estimate the water saturation. The log response must therefore be corrected for the volume of shale. By considering the influence that clay exerts on the entire suite of logs, your log analysis will provide you with a realistic estimation of water saturation.